Hello everyone! In our work, we present a machine learning approach to reduce the optical components in a time-shift time-of-flight measurement instrument, which is used for measuring particle size and velocity in a flow. The classical time-shift time-of-flight measurement instrument consists of two light sources and four detectors. The particles are detected one by the measurement instrument, and the size and velocity of each particle are calculated from the four light scattering signals from four light detectors. These light scattering signals result from the measurement of scattered light from a single particle passing through two light beams, which are formed by an optical systems in front of the light sources. The mathematical description of a light scattering signal shows that a single signal contains enough information to calculate particle size and velocity. However, the practical challenge is the signal processing in the real time to capture all particles in a flow. For that reason, iterative and recursive signal processing methods with unpredictable computation times are not good. This means that, for example, signal fitting or similar methods are not allowed. To address this problem, we propose the use of machine learning approach. In this case, the computation times are comparable to a matrix multiplication. Moreover, the signal processing based on machine learning can be implemented in hardware like FPGA boards. This was the primary goal of this work. In our work, we conducted an experiment where particles in a spray were measured with a time-shift time-of-flight measurement instrument. The measurement instrument was modified to capture individual light scattering signals from all four detectors. The captured signals were first used classically to calculate the corresponding particle size and velocity using classical method. For that, peak position were determined and the distance between the peaks was used to calculate particle size and velocity. In the next steps, the values of particle size and velocity were connected to the light scattering signals. For example, the light scattering signal from detector A was connected to the particle size and velocity calculated from all four signals using classical method. As a result, we get a signal with two connected values, particle size and particle velocity. This was similarly done for the signals from detector B, C, and D. Once the light scattering signals were connected to the particle size and velocity, they could be used to train a machine learning model. A regression model based on a neural network was used for this purpose. Two models were trained for each detector A, B, C, and D. One model for particle size and one model for particle velocity. After training, the models were saved and reloaded for prediction. The results of the prediction for individual particles are shown in diagrams 1 and 2, where the measurement values of the classical calculation methods are superimposed with the predicted values from the model. If the models had perfect prediction, all points in the two diagrams would lie on a line. To obtain better results than those presented here, a detailed analysis by machine learning experts and possibly additional measurement data would be required. In our work, we did not focus on evaluating various machine learning models to achieve the best score. Instead, our focus is on demonstrating the process of how this can be achieved. In diagram 3 and 4, the distribution of measurement values from diagrams 1 and 2 is shown. There is only a small deviation between the measurement values from the classical calculation method and predicted values from the machine learning model. As a conclusion, we can say that in this study we demonstrate the possibility of using a machine learning approach to reduce the number of detectors and light sources in a time-shift time-of-flight device. The prediction of our models show good agreement with the experimental data and consequently validating the proposed method. Thank you for your attention.